Morning, everyone. So in this lesson, we're going to be touching on two separate topics. One of them is this MOT, which stands for Molecular Orbital Theory. Basically, this is the last layer we're going to add to it. So far, we've started with the Lewis picture. Lewis picture is sort of a simplification from the Bohr model, only focusing on the valence electrons. The symbol would be used to hide the core as well as any core electrons. We then applied a very simple principle here called VSEPR. VSEPR had this notion: when you look at one central atom at a time, you find out how many electron domains are around that center. The place there is negative. Negatives hate each other, so they're going to push each other far away so that the bond angle is maximized and therefore the repulsion is minimized. We found that we ended up with angles like 109.5, like 120 degrees. We found out carbon was able to make 4 bonds, and that really didn't jive very well with our SPDF, what we call our modern quantum theory. Sort of orbitals and electrons only taking on a position when someone actually makes a measurement. And in a lesson a couple of days ago, we used hybridization to basically bring these two models back together. Hybridization was basically this idea that before something actually bonds, so for example, let's take carbon again. So carbon had this configuration 1s2, 2s2, 2p2. Before carbon actually tries to make a bond, let's say carbon is bonding in methane, before it's making 4 bonds here, we see a couple things happen. This carbon here actually promotes an electron up. It'll cost it a little bit to bring it to a higher energy state. At least I have 4 unpaired electrons, but before I can actually do any bonding, I don't actually bond with just my regular old p orbitals and my regular old s orbitals. What ends up happening is I end up trading in. The number of orbitals I trade in will match up with the number of orbitals that I get out of it. Those ones there will be intermediate in energy, somewhere between the s's and the p's, and depending on what I actually blended in, I would call it, in this case here, sp3, because I traded in one s orbital and the triplet p orbitals there. Each of these orbitals themselves is called sp3. So Pauli says every orbital can only hold 2 electrons. Because I had 4 unpaired electrons, now I have the 4 unpaired electrons that I need in my regular old SPDF model. Remember, there was a lot of math behind the scenes. You just basically need to know the definition of hybridization. We're mixing atomic orbitals. We're mixing our regular S's, P's, maybe even the D's sometimes come into play for expanded octets, but we're mixing those into blended orbitals. Some other features of this, again, I already alluded to here. The number of orbitals that you trade in is exactly the number that you get out. The energy is going to be intermediate, and then somehow the bonding and the angles will match up to those in VSEPR. VSEPR was so easy that it actually, even though hybridization has a lot of math inside, if you can do the VSEPR, if you can tell me the electron domain geometry, I can basically match up, oh, if you are tetrahedral, I know you're sp3. If you're trigonoplanar, I know you're sp2. So that was a layer of hybridization. It sort of represented this blend. Today, as I was trying to introduce to you here, was MOT. MOT is one new layer. Last day when we started looking at single bonds and double bonds being implications of sigma bonds and pi bonding, we actually started doing hybridizing one more time. We don't just hybridize for a single carbon atom. We then say, well, what if I had another carbon atom? That one could also be, say, sp3 hybridized. What if I now take the sp3 from the carbon on the left and I blend it, same sort of math, same sort of addition that goes into hybridizing, but what if I start blending two people's orbitals together, and then I end up with what we have saw, carbon can end up forming, say, a sigma bond, and now that sigma bond actually belongs to both elements, and in that case there, we call this one here molecular orbital theory. So that's why I shorthanded MOT earlier. This part here does get really, really technical. We're only going to get a quick taste of this one here, but what I want to just sort of show you is it's like hybridizing again, but it's just blending. Now I blend more than one person's orbital together with the same sort of math. I add up those wave functions, and I now end up with a molecular orbital like sigma, like a pi bond that now belongs to both of them. So as electrons, I used to have electron, in this sp3, or the carbon on the right side here had an sp3. Now I can have both electrons sitting in a molecular orbital, a sigma. What we're going to see today a little bit, it's going to be called a bonding orbital. So that's sort of the direction that we're headed. Again, we're only going to get a really quick taste of this, and then as we go through this, we'll have a look at what we need to actually know for this section. After we do molecular orbital theory, we're going to switch over to a totally different topic on polarity. We're going to backtrack to looking at our Lewis and our Vesper to try to figure out what it means for molecules to have polar bonds, to have uneven tug-of-wars, and especially we're going to look at the geometry, the 3D shape. Sometimes the tug-of-wars end up canceling out. We're going to say it's non-polar. Sometimes they don't. We're going to call that polar. So the goal in this lesson here is to touch on those two side topics here. These two side topics here are unrelated, but we'll do them in the same lesson here. So first side topic here, this one here is the more technical one. I already wrote down for you here. This guy here is molecular orbital theory, or MOT, M-O-T. Essentially, this is the notion here. If you want to form a molecular orbital, this blending between your atomic orbitals, molecular orbitals can be formed, and again, they always like you to know this acronym, although I've never seen this on any given test. Molecular orbitals can be formed by what's referred to as a linear combination of atomic orbitals. And the IB syllabus here would shorthand that LACAO. So far, let me just sort of sift through this here. So far, really only in this chapter, we need to know that our molecular orbitals, those are our sigma and pi orbitals so far. We'll flesh it out a little bit more very shortly here. They can be formed from what are called linear combinations. Linear combination in math class just means, a simple plus or a simple minus. There's no squares or anything like that. But what we're blending together this time is we're taking those atomic orbitals, we're taking the SPDF that every element itself used to have, and we're actually blending two people's orbitals together to form orbitals that now belong to both of them. So let me just show you this with the example of hydrogen here. Even our Lewis models and Vesper models accurately predict hydrogen, so it's not a problem. So I have H2 here. So far, we always start off with Lewis. H is an incomplete octet. It doesn't necessarily need 8 because it's the first shell. It only needs 2 electrons on that first shell. Configuration wise, this is 1s1 and this is 1s1. And now what I'm going to do is I'm going to think about doing a blend. Again, even my regular old Lewis model predicts this well enough, but as we start getting newer theories, we want to make sure it's always consistent with older models. And here's how this is going to work here. We're going to start off with the energy level diagram. I have 2 hydrogens. I'll say the hydrogen here on the left side. Let me color code it blue for you here. The hydrogen on the left side here currently has a 1s orbital. It by itself already had this 1 valence electron. The carbon on the right hand side here, in a similar fashion, I have hydrogen. Again, 1 valence electron. It also has 1s orbital, and it also has 1 filled. So that's just plain old hydrogen. We saw even for hybridization, I didn't need to blend anything because I can represent whenever 2 atoms connect, they're always going to be linear. But what we're going to do is we're going to now do this blending. And here I'm going to just hint at some of the math that you're going to do. For example, here, there is a wave function that represents the 1s orbital. So there's an equation that represents what the electron is doing when it is shell number 1, when it's spherically symmetric in this s orbital. There again is a wave function for the other 1s. Those wave functions here would be identical. And what we're going to do, again, lots of math behind the scenes, is we're going to pre-blend them. I'm going to blend in 2 orbitals. So I'm going to mix in the wave function for 1s1 and the wave function for 1s on this side here. I'm going to blend these 2 together. And my math is going to actually give me a sigma 1s orbital. Sigma is my molecular orbital. Its electron density is between the 2 centers. And it was made by adding up the wave function for the first 1s, for the blue hydrogen, adding up the wave function for the other 1s. Again, there's a lot of math behind the scenes. These equations here are very, very scary, but this is just showing to you the linear combination. It's basically blending again, but it's taking the blue guy's orbital and adding it, combining it together with the, on the right-hand side, the black atom's orbital. So we mix those 2 together. This one here is going to be referred to as a sigma. We've already said that. It's between the 2 centers, but this is going to be called a sigma bonding orbital. When things are able to make bonds, things are more stable. I mix those 2 together. Upon addition of them, I end up creating an orbital that's actually slightly more stable than the bits to become. So here this is going to be sigma 1s, and picture-wise here, what that looks like is we're going to have our blue hydrogen and our black hydrogen here. We're going to have a orbital. Again, we said it belongs to both of them. That's now called a sigma 1s orbital. Both electrons are now it's no longer just a blue orbital or just a black orbital here. Now both electrons are sitting inside that 1s. The electrons would end up filling in low shell and then pairing that electron up. So there we go, we get H2, we see paired electrons. Like we said, from this blending, even though the math itself is very complicated, when I trade in a certain number, I expect to get a certain number out of it. So because I traded in two of them, the other possible linear combination I can make is actually, if I take the wave function again, that same equation that tells the blue hydrogen what it looks like and the black one what it looks like, this time instead of doing a plus, right, that's a linear combination, the other linear combination is a minus. Right, so no squares or anything, linear combination is just simple plus, simple minus. Normally when you have an equation minus itself, you might think it cancels out, but these equations here are so complicated that when you minus it, not only does it not cancel, it ends up giving you an orbital that's actually higher in energy. Because this one here would have formed a sigma bond, I'm going to still call it a sigma. It was still formed between wave functions for 1s orbitals. That's a sigma 1s, but what I'm going to do is I'm going to add a star in the corner. Whenever you see that star there, what that star represents here is this is actually an anti-bonding, or I guess you can say sigma anti-bonding orbital. Anti-bonding means less stable, and therefore this orbital here ends up being higher energy than before. Right? So same as hybridization, when I trade in two, I get two out of it. When I do the plus, it becomes a bonding, more stable, it's less energy. When it's a minus, and it's becoming destabilized. And therefore, if I actually drew these out here, again, lots of math behind the scenes. We don't need to do the math. But when I actually do this here, we end up having our anti-bonding orbitals look something like this. The orbitals actually have what's referred to as a nodal plane. There's a place between the two hydrogens where the electrons will never actually appear. So there's no density there. Although there are two lobes, this is just one orbital. If I had electrons occupying this one here, I would end up having electrons in either of these rooms, maybe two on the left, maybe both on the right, or one in each one. So we're doing a really broad stroke with molecular orbital. We don't really know this too much, but basically what I want to show you here is it's like hybridizing again. It's like a lot of the math of blending. However much I trade in is however much I get out, but this time the blend is not just between one single atom, that was called hybridization. I'm going to actually blend two atoms orbitals together. Whenever we do the linear combination with a plus, it becomes more stable, bonding orbital. Whenever we do it with a minus, it's called anti-bonding, and it's destabilized. So sigma and pi bonding, and now we've introduced that notion of having a bonding orbital and an anti-bonding orbital. I'm going to link you to a clip on the lesson here. It's going to demonstrate to you, he's going to actually start off with a sample of liquid nitrogen. He's going to pass the nitrogen between two magnets, and he's going to see basically the nitrogen falls directly through the magnets. It demonstrates that nitrogen is not magnetic. What he's going to do is he's going to make a sample of liquid oxygen. Oxygen is usually a gas. Using liquid nitrogen, he actually cools the oxygen and actually liquefies. Really cool to actually see it as a liquid that we breathe. And basically what he's going to do is he's going to pass the oxygen between the two magnets as well. And what you're going to see is the oxygen here is somehow magnetic, and the oxygen does get stuck between the two poles of the strong magnet. So based on that demo here, we're going to try to explain it here. That's what we see in real life. Science aims to come up with theories and come up with rationales of why that's the case. So in the YouTube that I'm going to link to you here, you're going to see oxygen being magnetic. In Chapter 3, we refer to that stronger attraction to the poles. We call that paramagnetism. We're going to explain this here. I want you to explain the paramagnetism of oxygen. And oxygen, when it's by itself, we knew it to be diatomic O2. So just good practice from Chapter 3 here. When things are paramagnetic, we remember this one here was a stronger force. Most things that were diamagnetic here had paired electrons. Even if you had one unpaired electron, that's what we're going to look for paramagnetism, that one impaired electron dominates, and it is actually an attraction. Diamagnetism would actually be a slight repulsion. In this case here, we're seeing the oxygen actually get stuck between poles. The same thing would be true for gaseous oxygen, but it's a lot cooler when we actually see it in liquid form. So our whole goal is to try to find oxygen's unpaired electrons, because if it's able to have unpaired electrons, it's able to be paramagnetic. Let's start off from scratch here with our Lewis. So oxygen has a configuration here, 1s2, 2s2, 2p4. So we know all the inside shells are full. There's no unpairing there. P's come into us in sets of 3. So we're going to do our Hund's rule here. I go single, single, single. I do the pairing. At first, you might be like, oh, easy. Oxygen has the unpaired electrons. It's already paramagnetic. But remember, oxygen here is actually a diatomic. Oxygen is actually paired up. So imagine I actually had two oxygens having this configuration, exactly the same 1s2, 2s2, 2p4 notion. And what's going to happen here is with the highest shell, we're going to end up having these unpaired electrons actually bond together. That's actually better represented with the actual Lewis model. Oxygen being in column number 16, we go single, 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 single. I'm going to pair up two of them. Single, 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 single. Pair up two of them. Because things are unstable when they have unpaired electrons, they're going to very quickly want to pair up this electron. And essentially, in this case here, we see by pairing one, it's closer to a full octet. Actually, by pairing both of them, it's now going to be satisfied the octet. And our Lewis model here, typically we'd use this stick model here. Be careful for a Lewis diagram, you have to have all those outside dots. So there we go, we have a double bonded. So far what would have saved the day and we had unpaired electrons, it actually ends up being sigma bonded, not great. So we actually need this layer here of hybridization to actually try to figure this out. If I just did hybridization would just take a look at one carbon at a time. It would say, well, this oxygen here has 3 domains. I would have hybridized, let's say, sp3 and sp3. So that would be sp3 there. The sp3 hybridized, blended together with the sp3 on the other side. That one there would have given you a sigma orbital, and then your p orbitals here that are up and down from the plane here would end up giving you a pi orbital. That so far is just consistent with what we did before, but everything there still looks paired up. I still don't get that unpaired electron. So we finally need this molecular orbital theory here. I'm using it with the example of oxygen here. You don't need to know too much of the theory behind, but I'm just going to show you how this works out. For oxygen, similarly, oxygen is going to have its 1s orbital. I'm not going to bother drawing this because that's going to be on the inner shell. I'm going to start off from the outermost shell. I would expect that inner shell will be filled. So I'm just going to look at shell number 2. Shell number 2 for oxygen, there's the oxygen on the left side and the oxygen on the right side. Shell number 2, each oxygen has an s orbital. I'll call it a 2s here. The other one here, this one also has a 2s. It also has 3 p orbitals here. I'm going to draw them a little bit higher. Those are energetically further from the core. So I have a 2p orbital and I have a bunch of 2p orbitals here. And then essentially what we've been saying is we've been blending the two guys' orbitals together. So here the math behind the scenes is you take the wave function that represents 2s, the wave function that represents 2s. We're going to do that same math. This time we're going to get the bonding orbital for 2s. Again, the wave function would just be add the 2s on the left and add the 2s on the right-hand side here. That's an add, so it becomes more stable. This one here is going to end up forming for us a bonding orbital for us. Right? If we did the opposite combination, if I did sigma 2s and I did a wave function and I did a minus the wave function, so this guy's orbital and this guy's orbital, but I did a minus, we saw earlier we ended up getting an anti-bonding orbital. Let me just label these for you here. This one here is a sigma 2s, that's bonding, and then we have a sigma star 2s. Right. So oxygen in both cases here, the same thing would happen to the 1s orbital. In both cases, oxygen actually has a 2s2. So imagine you have the electrons filled up. Now the oxygens don't have their own orbitals anymore. Now they have these together orbitals, these molecular orbitals. There's 4 orbitals. I'm going to do my off ball. I'm going to go single, pair it up. If I have 2 more, I'm going to end up getting the higher one and then the top one here. So even though I know the anti-bonding orbital is less stabilized, well, I only have those rooms here. Once the lower shells are filled up, sure, I'm going to fill up the higher shell. More interestingly, what's going to happen is with the p orbitals. So again, I'm just going to do a little bit of hand-wavy math here. The p orbitals, we know it geometrically, they are sort of dumbbell shaped. Let's say this is a px orbital, and then we have a px orbital on both sides. So I'm using the px here because let's say the x-axis is pointing horizontal between the two of them. In that case there, I'm going to do this sort of similar fashion. I'm going to try to take the wave function of a 2px orbital, and I'm going to add it to the wave function of a 2px orbital. It's like adding a dumbbell like this and adding a dumbbell like this. You'll notice that the electron density will be between the two centers. That similarly is going to end up giving me a sigma orbital. So in this case here, I'm going to get a sigma. It was formed from 2p orbitals, so I'm going to call this a sigma 2p orbital. That's stabilized. So I'm going to do a little bit lower here. Should have left myself a little more room. So this in the green here, that's called a sigma 2p. If you want to emphasize 2px orbital, that's bonding. And similarly here, if I had the minus, if I had the less bonding one here, it would form a nice symmetrical complement. It would form a sigma star, the anti-bonding form of 2p up here. I trade in those two. I expect to get 2 out of them. One of them is a plus bonding. One of them is a minus, which is anti-bonding. The other piece here, do something a little more interesting. When those p orbitals here, px was on center, I have a py that potentially is maybe in and out based on my axes here. When those two orbitals get close together and when they add up, they're actually going to be off the internuclear axis. If you remember from our previous chapter, previous lesson, we would call that a pi orbital. And what we're going to end up with is we're actually going to get a pi 2p orbital. And a pi 2p orbital would be like sigma of a 2py, and I'm going to add a sigma of a 2py of the other orbital. In all of this, I'm blending the orbital on the left side and the orbital on the right side together. Similarly fashion here, plus makes it more stable. I get a pi bonding orbital. If I do the minus, I'm going to get a pi star anti-bonding orbital. So when I take the py and the py on this side here, one of them will be stabilized. We're going to call that one there a pi 2py. When I do the subtraction, I'm going to end up with a pi star, an anti-bonding version of it. Still a linear combination, it's still doing a lot of math. And exactly the same thing happens to the purples. Purples, I'm going to, brown, I guess. Brown, I'm going to represent as the PZs. The PZs, when they potentially overlap up and down, they also are going to end up as a pi bond. So when I add them together, that's going to give me another bonding orbital that's stabilized. So that one there will be called a pi 2pz. When I do the subtraction between them, I get the anti-bonding version. Yes, I definitely want to fill up lowest energy first. I fill up all the bondings before I fill up anti-bondings, but if you really have that many electrons, you will have to start filling up those anti-bonding orbitals. So pi star with the 2p. The reason why this gets to be really, really complicated, if it's not complicated enough here, this is the diagram, this is the splitting pattern for oxygen. If we did the very same thing for nitrogen, we would get the same orbitals. I get some bonding orbitals, sigma and pi, and then the anti-bonding versions, but then we're going to see that the energy levels are actually spaced a little bit differently. Sometimes the pi stars actually end up higher than the sigma star. That's actually going to depend on the exact element that we're talking about. Again, for us, what we care about, we just care that sigma and pi bonding are molecular orbitals, and they can be formed from linear combinations, simple pluses and minus, between orbitals on the left-hand side and the orbitals on the right-hand side. So let's finish off our question here. Oxygen here by itself, we did our Hund's rule, single, 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 I paired up. Both of them actually had a 2p4. I have 8 electrons that I need to fill into this middle part of the diagram. Watch me do a Hund's rule here. We're going to go single, single. First two are paired up. I have the pi 2py, the pi 2pz. Those ones are degenerate. I'm going to have single, single. I'm going to do the pairing. And I have 2 last electrons here. I maximize all my bonding orbitals. Those ones are the more stabilized ones. You can look up a diagram for what these shapes actually look like. And then we're going to actually have 1, 2. Because I have 2 degenerate orbitals, we have our answer to the question here. This is how oxygen has its unpaired electrons. This is how oxygen is actually going to be magnetic in the form of paramagnetism. All right, so all that to explain what we saw in the YouTube clip here. The oxygen actually gets stuck between the 2 poles of the magnet. If you go on into chemistry here, there's one other thing that we can talk about based on this diagram. We know oxygen ends up as a double bond. In our resonance section, we had defined something called bond order. This was defining a number that represents how many bonds are between the 2 of them. In this model here, anytime we come up with a new theory, we want to make sure it's consistent with older theories. The bond order can be found with this molecular orbital theory. Find the number of electrons in bonding orbitals, so bonding electrons, minus the ones in anti-bonding orbitals, and then divide by 2. So how that would look like this time here, I know, just don't worry about the 2s, okay, because I'm worried about the outermost shell here. If I'm just looking for the p electrons, what are they doing? I have 6 electrons that are in bonding orbitals. 2 of them in sigma, 2 of them sigma, 4 of them in pi. So I have 6 of them that are bonding. I have 2 electrons that are in the anti-bonding one. So 6 minus 2 would give you 4. You do the divide 2, and now the bond order is 2, and that's consistent with the fact that a oxygen here is actually double bonded. So that's where we're actually going to leave off our sort of bonding theory. It gets to be really, really complicated. Let's just totally switch gears here, and let's just finish off this lesson here, switching over to polarity. All right, Polarity in comparison here will be a lot simpler than what we just did. Polarity we already introduced previously. We saw how bonds themselves could be polar. We saw that ionic and covalent are going to be sort of two ends of a spectrum. Remember, it was just a nice hint for us, metal, non-metal. Really, that really wasn't the definition. But it turns out here, if I took a metal and a non-metal, the metal, in this case here, sodium has 1 valence electron, chlorine has 7. First thing that has to happen is they have to collide. They can potentially actually share these electrons in a covalent bond. I would check the electronegativity table, especially if this was a paper 2 kind of question. The En for this one is 0.9. The En for the chlorine is a 3.2. I don't really care about the absolute electronegativities. I care more so about the difference in electronegativity. The difference is bigger number minus smaller number. This is 2.3. Usually we throw around a number of about 1.8. This is going to depend on that triangular bonding diagram that we saw earlier with the average energy, the average electronegativity. But essentially when the difference gets to be really big, the stronger competitor is pulling so hard that sodium completely loses the electron, becomes plus. Chlorine steals sodium's electron and ends up becoming an overall minus charge. That's when I get a full plus and a full minus. We end up getting the lattice, we end up getting ionic. Let's compare that to the case here of, let's say, chlorine against chlorine. So chlorine is halogen. They have 7 valence electrons. In this case here, they both happen to have very high electronegativities, 3.2 and 3.2. It's the difference that we care about. The difference here is actually 0. The tug of war is actually fairly even. So this time here, it's a perfect sharing, covalent represented sharing. So we represent this as sort of the extreme. If the electronegativity is 0, we refer to this as a non-polar sharing, non-polar bond, non-polar covalent. So that's a 50-50 splitting, perfectly even. What I want to emphasize in today's lesson here is actually emphasize, well, what about the in-between? What if I'm not quite to the point of a difference of 1.8 and becoming ionic, but what if I'm somewhere in the middle here? Let's take a look at an example. Let's go oxygen against Cl. Right? Actually, let me make it a little more, maybe more dramatic here. Let's go, I don't know, nitrogen against Cl. So N, Cl, single bond. So let's have a look at our data table here to take a look at their values. So let me actually make this even more dramatic here. Really should think about my questions before I ask you them. So let's say PCl here. With this one here, check your electronegativity table. P has a different has an electronegativity of 2.2. Chlorine similar has a difference of 3.2. I just wanted to choose a non-metal that was a little bit far away here. The difference in electronegativity is 1. It is uneven, and it is actually in favor of the chlorine side. Chlorine is the bully, and chlorine actually hogs the electron. So these two electrons here, they spend more time with chlorine on the left side. We're going to represent in this section here using dipoles. Dipoles always point towards the winner. Even though we're not pulling hard enough to completely rip the electrons off, the electrons are spending a little bit more time with the chlorine. And what we end up with is getting a separation of charge. That's what this dipole shows you. I point towards the winner. This side is kind of negative. Where this hash is here, it's actually going to be kind of positive. So we get a slightly uneven bond here. Instead of a 50-50 split, I might be a 30-70 split. Two interpretations. You can interpret it as, yes, I know a single bond here is 2 electrons. You can interpret it as the 2 electrons sit closer to the chlorine than the phosphorus. Or a more correct interpretation is electrons are constantly bouncing around phosphorus and chlorine. And what we're going to end up with here is we're going to have the electrons spend more time with the chlorine side than the phosphorus side. What we created here is called a polar covalent bond, or just simplicity here, a polar bond. A polar bond is given by, we see it in this case here, whenever we have some difference in electronegativity, whenever there's some unevenness, there's going to be unequal sharing, and that's when we end up with this polarity. We end up having a dipole, and this dipole points towards the winner. The dipole is a separation of charge. It says that, oh, one side is actually more negative than the other side. That's what it takes for a bond itself to be polar. We can just make one last sort of extension here. What if I want a molecule to be polar? So for molecules, entire molecule which has multiple bonds here, molecules are polar. This is a simplification, but this is the one that we'll go with. Molecules are polar if you have 2 conditions. The first condition here is, well, we want to be polar. We definitely want to have polar bonds. If all my bonds are non-polar, it's hard to be polar. right? So I want to have polar bonds. We just said for this one here to have a polar bond, I need to have a difference in electronegativity. And in fact, the bigger the tug-of-war difference, the bigger the electronegativity difference, the more polar something gets, but at least I have to have that polar bond. The second one here, seemingly a little strange here, is I need to have some sort of asymmetry in my geometry. Sometimes if I get pulled evenly, sometimes the dipoles end up canceling out, and therefore we're actually no longer polar. So let's just look at a couple molecules just to finish off here. This part here is not meant to be very hard, but we're going to study molecule by molecule, figure out whether you have polar bonds, and based on your geometry, figure out if they cancel or not. So let's start off with the example of CO2. So a very common atmospheric gas here. We've drawn this a bunch of times here. You still need to do the Lewis. And if you happen to know the VSEPR sort of off the top of your head, I would draw it very symmetrical. I would draw it trying to represent the 3D shape because that's going to be important in this section. When I'm going to ask you this question here, is CO2 polar or nonpolar, we're going to study each bond one by one. If you have the table, of course, you can look it up. So carbon, I think it's an electronegativity of 2.6. I'm looking up table number, I think it's table number 8 for the difference here. And look at it bond by bond. We go bigger minus smaller. Oh, great. I have a difference here of 0.8. And that pulls towards the oxygen side. This side here is kind of negative. So that one there is definitely a polar bond. Those 4 electrons that make up the double bond are leaning more to the oxygen on the right-hand side. In a similar fashion here, we have a dipole on the left-hand side here. That one there will also say, well, the oxygen wins, and it pulls towards the side here. So do I have polar bonds? Definitely, yes. But let's worry about the geometry here. Carbon here, which has 2 domains, this actually is the correct geometry. We actually are a linear molecule. Now I want you to imagine this here. Imagine this were you, and imagine you were getting pulled evenly just directly across. So I am being pulled to the right and pulled to the left, evenly by the 2 oxygens. Both sides are trying to become negative because both sides are winning the carbon. In this case here, if I'm getting pulled evenly, I'm going to say, well, those 2 forces will actually cancel out. In our physics, we would say the vectors here cancel. And basically, because those arrows canceled out, even though I do have polar bonds, that's still going to be important for our IR spectroscopy stuff next year. But overall, I'm getting pulled evenly in both directions. I can say here the dipoles cancel. Another way of saying that is there's no net dipole. There's no overall dipole. There's no unbalanced force. There's no unbalanced arrow. And therefore, even though I do have polar bonds, this molecule here is actually nonpolar. Based on the symmetry that I have, if I'm symmetrical, it ends up canceling out. Let's do 2 last molecules here. A lot simpler, hopefully, than the molecular orbital theory stuff that we just did earlier. Let's draw water. Again, you have to do a Lewis model before you can do anything. You can check the electronegativities, or you can just use a trend. The closer you are to fluorine, remember in paper 1 you don't have the full data booklet. The closer you are to fluorine, the more electronegative it is. Oxygen is going to be the hog. Oxygen is going to steal the electrons towards itself, and it's actually going to make polar bonds. So far, if I look at the water molecule here, so far, if this were me, and if this truly were the geometry, I'm getting pushed to the right and pushed to the left, exactly the same strength. I'm going to say dipoles cancel, nonpolar. And yet we've been going through this course and we've been saying, no, water is polar, water is polar. Because it has the positive and negative and it's able to stabilize transition metals, things like that, something is wrong with our picture. See if you can identify what it is here. This is why we had to actually do the VSEPR lesson before this. We actually learned that for VSEPR around the central atom, VSEPR depends on the electron domains. So the Lewis, even though we don't actually care the geometry, many times you will see in textbooks it drawn like this. If I have 4 domains, I want you to remember that having 4 domains is sort of like this, it's based off a tetrahedral sort of geometry. Or if I just sort of look at it perspective on here, it's just going to be like this. And this one here would be tetrahedral by itself would have been 109.5, but because the lone pairs themselves are diffuse, every lone pair that I get will squeeze the leftover bonds tighter. Water actually has a bond angle of 104.5. So this actually is the better geometry, the real shape of water. This time, if you have the dipole, oxygen wins and oxygen wins. If you do some vector analysis here, sure, there is going to be an inward component that ends up canceling out, the rightward and the leftward. But you see that both arrows themselves are actually pointing upwards, and oxygen here is actually going to have a slightly negative end and a slightly positive end. That's what ends up making our molecule polar. So phew, water is still polar. Let me do one last example with you here. Afterwards, you can go back through your lab here, go look through all the molecules and just define for yourself, is it polar or is it nonpolar? So this is essentially the methane molecule, also based off a tetrahedral. Pretty much when we start getting into such fancy geometries like 3D, tetrahedral, trigonal bipyramidal, the shape itself is set up to cancel. In this case here, we got some unevenness because of lone pairs. We're going to see the unevenness here for this fluoromethane here. So I'm going to try drawing it. I'm going to draw it with the Vesper. So CH, I'm going to use that wedge and dash notation because I want to represent it in 3D. Hopefully you can see that tetrahedral better as you practice this. Again, the question is simple. Is this polar or is it nonpolar? You want to look for the electronegativity differences. I just gave you an example of a molecule with CNH because this one comes up very often. A lot of organic chemistry molecules are CNH. Carbon, I know, has an electronegativity 2.6. Hydrogen has an electronegativity 2.2. This difference here is actually 0.4. It's not 0. It's not perfectly 50-50. But what we're going to say is, since this difference here is so small, since the difference is so small, so I'm thinking here, not 50-50, but maybe like 49-51. Yeah, we have a slight leaning towards the carbon side. But really, when I actually look at molecules, this behaves like other nonpolar molecules. I'm going to just ignore. So this bond is nonpolar. So that basically helps us cap it here. If I look at this polarity spectrum here, I had upwards of about 1.8 to become ionic. 0.4 here is our carbon-hydrogen. That's going to be nonpolar. I'm really focusing on differences between about 0.4 and 1.8 that actually are polar enough that can actually give me these dipoles. Whenever I see a CH, I just totally don't worry about it. So when I'm looking at this one here, I would say, well, these bonds here, they don't give me enough of a difference to become polar. But when you fight C against F, F is a straight 4.0 here. This difference here is a whole lot bigger. There is a dipole. I point towards the winner. This difference here, big number minus small number, is a 1.4. So it's a slight imbalance. It's actually a really big imbalance here. And fluorine hogs the electrons. This is a polar bond. Had this one here been methane, had this one here been carbon with 4 hydrogens on the opposite ends, or even tetrafluoromethane, if I had fluorines on the opposite ends here, the shape, again, is set up to cancel out. If I were being pulled in all these directions, it would have canceled. But in this case here, the asymmetry actually comes from the fact that only one of these arms here has a dipole. The other arms here don't have any dipoles. So even though the shape is set up to cancel, that gives me my asymmetry. So therefore, this one here is actually a polar molecule. In fact, the more fluorines I end up with for this molecule, the more fluorines I end up with, let's say I go from one fluorine to another fluorine, now I have another tug-of-war here. The more tug-of-wars that I have, with the exception of the tetrafluoro one, that's nonpolar, we're actually going to get increasing polarity. So see if you can go back through your lab here and just assign whether something is polar or nonpolar. In our next lesson, we're going to see something more with polarity. Thanks, guys.